There are significant limitations to the Arrhenius definitions for acids and bases. One limitation is that the Arrhenius definition says that you'll produce H plus and OH minus ions in water. But what if you're not in water? Another limitation is that the Arrhenius definitions for bases is not deep enough. For example, ammonia, NH3, is a great base. It's often used in cleaners like Windex. But when we look at the ammonia molecule, NH3, there is no hydroxide. It's a base, but doesn't have OH. We need to go deeper. So a more encompassing definition for an acid nor base is the Bronsted-Lowry theory. I call it my BLT. This theory says that acids will donate or produce H plus ions, very similar to the H plus definition or the Arrhenius definition. Now, your Bronsted-Lowry definition for a base, however, is different. A base does not need to have hydroxide in it. Instead, your base simply must accept an H plus ion. And in order to do this, your base must have a lone pair of electrons you can stick that H plus ion. So again, the BLT theory, acids donate H plus, bases take in H plus ions, and they have a lone pair that they can do this with. Let's go through a couple of examples. In the first generic example, I'm going to take an acid, HA, H with all the rest, and put it with a base, B, that has a lone pair. The H plus ion will leave my generic acid HA and go on to the lone pair of B. That will generate two things. It'll leave behind the A minus once we took off the H plus from HA. And then we will generate a protonated base, HB. We have the base, but we added an H plus, so now it's HB with a plus. Let's look at a more specific example. What if I started with hydrochloric acid, HCl, and put it with our weak base, ammonia? The H, the proton, will leave our HCl molecule and go on to the lone pair of ammonia on the nitrogen atom. Now, if we remove an H plus from HCl, that will leave behind Cl minus. Then, if we put on an H plus onto our NH3 molecule, well, now we'll have NH4 and a plus overall. So that's an example of a Bronsted-Lowry reaction between an acid and a base. Now, acids donate H plus ions and bases accept those H plus ions. There are some substances which can do both. Just like people who write with both hands are called ambidextrous, or animals that can live in water and land are called amphibians, these substances that can both donate H plus ions and accept H plus ions, they're called amphiprotic substances. Now, here's some examples of them. HSO4 minus is an example of an amphiprotic substance. The bisulfate ion can accept an H plus. It's a negative thing. It would love to bond to a positive H. If it accepts an H plus, it's going to make H2SO4. But HSO4 minus is actually a pretty good acid. It can donate that H plus to make the sulfate ion, SO42 minus. The same thing can happen with the bicarbonate ion, HCO3 minus. HCO3 can accept an H plus to make H2CO3 carbonic acid. It can also donate an H plus to make the carbonate ion, CO32 minus. Those are good examples of amphiprotic substances. But perhaps the best and most important amphiprotic substance that you'll encounter in acid-base chemistry is water. Water is an amazing amphiprotic substance. Water can behave as an acid if you put it with a base, or water can behave as a base if you put it with an acid. If water acts like an acid, it can lose an H plus ion because that hydrogen is attached to an electronegative oxygen atom. If water loses an H+, it forms hydroxide. On the other hand, water can function as a base and take in an H+ ion. If it takes in an H+ ion, it forms hydronium, H3O+. You're going to encounter water coming up in many of your future lessons. It is an amazing amphiprotic substance. Hope that helps.